back. So now we're going to have shorter presentations by the LCLS scientists. Yeah, so everybody's going to introduce themselves.
All right, thank you. Can you hear me? Is this working? Okay. So, all right. So this is going to be a bit of a whistle-stop tour between a whole bunch of us, walking through the LCLS facility as it exists today, and as we hope it will exist in a couple of years. So, assuming the team does its job. What I'm going to do is give you a very quick overview of where we've come with LCLS, a quick view into LCLS-II, and I'll finish on a few observations of common mistakes people make when they're putting proposals together. So, which all will seem blindingly obvious, but they're made again and again and again and again. Okay, so, all right. So I guess the first thing to say when thinking about LCLS is that the headline characteristic of LCLS is its peak brightness, its peak brilliance of being 10 to the 9 or 10 to the 10 times brighter than a traditional storage ring. But actually the most amazing part of it, I think, and the aspect to focus on when really designing and thinking through your experiments is the degree, not the degree to which it's a flamethrower that can deliver incredible high brightness beams, but the degree to which it can be tailored. And I think a very large part of our job in the facility is to respond to people like you to think through how do we want to tailor it further going forwards. Just some examples shown here, on the top left, to go from what has been a traditionally linearly polarized beam to now in the soft X-ray up to about 1.2 kilovolts, to be able to arbitrarily choose the polarization all the way up to what, like 99 and a bit % purity in the in circular polarization, and be able to spatially separate the polarization so you really do get that purity. Let me drop down here, perhaps on the bottom left, the ability in certain spectral regimes, both soft and hard, to introduce a self-seeding beam. So to go through the first set of undulators, set the photons on their way, and pick out a particular color to seed the subsequent amplification. So that rather than getting the traditional, very spiky, broad bandwidth, 10, 20 eV SASE spectrum, you can get sub-EV, very robust spectral selection, albeit, of course, the intensity still bounces up and down. And moving forward from this, perhaps in the future, to get, as they do with Fermi at Electra, an external seed that has a coherence to it, so you're not growing from noise, but you're growing from some well-defined spectral selection. This both gives you the ability to live very close to the Fourier transform limit as you scale up and down in pulse length. It also, of course, increases the spectral brightness by an order of magnitude or so, for those who care about that. You can then adopt any one of maybe 6 or 7 different techniques for having X-ray pump, X-ray probe, or X-ray probe, or pump, separable and locked dual X-ray pulses, in which there's reasonably independent control of the temporal and energy separation. Energy separations are currently limited to quite a small level, tens of eV level. In LCLS-II era, it's almost arbitrary separation. So you can go from one edge to another edge, say carbon and oxygen, or oxygen and nitrogen, or what have you, and even select one of these to have a different polarization. And so this has proven to be incredibly valuable for chemically specific monitoring of an evolving system, where one line and another sit on different elements within your system. Where this has been going more recently is multiple pulses, so 4 or 8 pulses that are locked within the S-band cycle, so that's about 350 picoseconds separation, all the way up to many hundreds of nanoseconds. I think maybe the record now is 600 nanoseconds, so a good fraction of a microsecond for those who care about long timescale dynamics, such as in MEC era. And then, a lot of work over the past couple of years in pushing the coherent bandwidth up and the pulse length down. Here just a couple of examples that were published a few months ago, maybe half a year ago now. Getting in the hard X-ray regime, 5 to 9 kilovolts, around about 200 attoseconds, at least inferred from the spectral width, roughly 50% of the time, getting a single isolated spike like that, and in other times getting dual spikes or multiple spikes. Most recently, on the soft X-ray domain, using the so-called X-sleep system, getting down to coherent bandwidths of what now, 4, 5, 6 eV, somewhere around there, and so the few femtosecond or maybe sub-femtosecond level at a few hundred eV, for which the peak power of these systems is still high, even though the pulse energy may be somewhat limited. And then this is complemented by active development of whether it be synchronization tools. Nominally we sit around 100 femtoseconds or so jitter, and then time bin using time tools, trying to get that robustness of the solid locking of the system down to 10 femtoseconds or so with LCLS-II. So there's many ways in which this beam can be tailored, and I think the art of doing a great experiment is to think through how you harness that and tailor it to your particular problem of choice. All right, so moving on from where we've been to where we're going, there's $1 billion or more going into the so-called LCLS-II project. The thing we're worst at is acronyms, and so LCLS-II is now over 2/3 complete. There's more than half of the cryo modules have been manufactured by Fermilab and Jefferson Lab, and they're starting to be shipped to us over the summer. This takes us from 100 hertz, 120 hertz to a programmable set of pulses with a arbitrary spacing up to about 1 megahertz. We throw away that beautiful undulator hall that we have today and put in place 2 new variable gap undulators, one soft, one hard, which will then of course allow dynamic tuning of the X-ray color, of the X-ray wavelength, as you're doing your experiment, as if you want to follow through a particular edge perhaps, or if you want to track one edge versus another. And to first order, it roughly doubles the experimental capacity. My main job in life is disappointing and frustrating 80% of the people I meet because of the rejection ratio of LCLS. So hopefully I can make more friends, going forwards. We'll see. I think Mike and Georgi and Andy and company will talk about how we're modifying the near experimental hall. At the moment, there's not much modification to the far hall that Meng will talk about, but that will come with the so-called high energy extension and the even worse acronym of LCLS-II that hopefully will come mid-decade. At the moment, we're anticipating first light from the LCLS-II LINAC, this superconducting LINAC, somewhere around November-ish of 2020. That will bounce back and forth by a few months, depending how things go. And of course, we retain the copper LINAC, the 120 hertz LINAC, which will, even though it's not shown here, go to both undulators for high peak power performance. Graphically, this is what it looks like, of course. You've seen the curve on the left many times. This is peak brightness, where you get this factor of 10 to the 9 or so. LCLS-II gives us the added benefit that the fundamental, which currently gives out at about 12 or 13 kilovolts, will roughly double to about 25 to 30 kilovolts in the fundamental, and maybe push that with harmonics up to 40 or 50 kilovolts or so at 1% or less peak power. But the big advantage we get from LCLS-II is this increase in repetition rate, which gives us the factors of 8,000 or so increase in average power or average brightness, and in this very controllable continuous CW pulse train, as opposed to the 10 hertz, 4.5 megahertz bunching that you would see at Flash or European XFEL, and of course the 120 hertz we have today. What will this do for you? I think other people will give more detailed examples, but let me just give you 3 characteristics. Shown here at the top, can we take advantage of the ultra-fast nature, ultra-short pulse nature of this source with the ability to gain significant information on early stage charge flow, or for those people who care about strong field atomic science. Can we make use of where we see real limitations at the moment about integrated signal? Here showing some examples from LCLS over the past couple of years, this carbon pentanyl system where we're really running out of juice. So can you take advantage of the high repetition rate to build up these very complex, say, multidimensional spectroscopy signals? And then finally, can you use the high average spectral brilliance of the machine to really get extremely high resolving power, maybe 30,000 resolving power or more at a kilovolt, and use that to probe material science dynamics down at that level where currently, if you try to do this on the synchrotron, you simply don't have the integrated fluence to do so. What this looks like in the near hall will be described in much more detail in a moment, but the beam coming from left to right, this is our current AMO area, SXR area, and XPP area. These two will be stripped out and completely reconfigured, and then we even send the beam upstairs to this on a monochromatic line that Georgi will describe. I guess just at a very high level, this is high field science. This will be the world's only dual X-file beamline, as you know, and then this will be this variable resolving power spectroscopy device. So here in my final slide, some thoughts about common mistakes. Learn lessons from what we've done over the past few years in LCLS to see what works and what doesn't, particularly when it comes to proposing LCLS-II experiments. There's a number of experiments that we've done today that show a proof of principle, but really can't get the integrated signal, or you can't use a dilute enough sample to be physically meaningful, or you can't look at a system in operando, but you can use the information gained from the proof of principle experiments in order to inform LCLS-II. I think many proposals we see could so easily be corrected by just some simple and quick conversations with the kind of people you'll hear about in a moment to either utilize the performance of the machine appropriately or the instrument appropriately. Collaborate is the hallmark of LCLS. Teams range in size from maybe 10, I think our largest was 80 or so, which was fun. So bring together expertise where you can find it, and we look on that very positively. Many experiments get rejected at proposal stage because you could so easily perform some precursor experiments at a ring or a high harmonic source or ultra intense laser or what have you. Similarly, many fall over from the lack of a quantitative prediction of the signal you're going to make. Somebody will say, the panel will say, it looks like a great experiment, but I have no idea whether they'll actually see the signal that they're searching for. So model that as much as you possibly can, and we're trying to do our job of putting together a start-to-end model of the entire facility so you can use that as a backbone for your modeling. Make sure it's very clear what goal you're trying to achieve, and we want to go from proof of principle to actually solving meaningful and important scientific questions, particularly with LCLS-II. And be realistic. You'll get between 12 hours and 60 hours. Don't try and solve world hunger and world poverty all in 1 week. And then if you don't publish, you will die. All right, that's me. So, all right. Any initial questions? Otherwise, we'll delve into a bit more detail. No? Okay. In that case, I'll hand over to Mike Minetti, who is on the softer end of the human spectrum. Oh, sorry, the photon spectrum.
I think it's this one. You guys hear me? Yay? Nay? All right. Okay. So thank you, Mike and Amy, for the chance to speak, talking to you about LCLS-II. Just from background, as Mike said, I'm not just a softie. I am the soft X-ray department head at LCLS-I, as you see today. I think you guys are going to go on that tour for AMO and SXR. Those are the first two hutches in the line from the source, so hutch 1 and 2. And what you're going to see today, it's on its last voyage. In run 17, when we start here in September of this year, those by the end of this year and into late December and early January, they're going to be just removed for the instruments that you're going to see today. Make way for the new instruments that are high repetition rate capable. Because what Mike said the other, just right now was what all LCLS-I has been really good at is this really high peak power, coherent imaging. Hit it with a big hammer. LCLS-II can do that as well. But what it can do better than LCLS is in the form of spectroscopy. And then basically all those examples that Mike showed were heavily spectroscopic in nature. And we'll show you kind of like some science examples. I think all of us will show you what we'll be able to capably to do. I also wanted to say, in large part, the lead scientist, Peter Walter, is spearheading this effort. So I'm just here in his stead. He's on travel. But at the same time, not only being the soft X-ray department head, I'm the scientific director for the LCLS-II instruments. And so we have a little hand in say this. And so I'm just thankfully stepping in for Peter. This is all his work. and credit should be due there. So what Mike was showing, our turn-on time, and this is kind of very unique. It's not unique. It's just this is news. This is fact. And so where we see ourselves coming up in the early 2020 timeframe for early science and commissioning of our new instruments. And so as of right now, when we come in December, our soft X-ray operations for all of LCLS will cease until this time frame here, when we start bringing on our instruments here, except in particular with this source here, the superconducting RF. That is what LCLS-II is all about. In order to help preserve and help us get us in a position to commission fully our new instruments, we're going to utilize our 120 hertz capability that we have today to really iron out and make sure that we are hitting the ground running for our superconducting ops when we move forward with our 3 new instruments in this time frame. So we kind of find ourselves here, right about here. We have this short, brief run, both soft X-ray and hard X-ray operations at 120 hertz. But I think you're going to be basically writing proposals for this series of experiments here for LCLS-II. So this 250 EV to about 5 kilovolt operating range in these various instruments. And so what are we going to be building you? I'm here to talk about the TMO hutch. The time, I always get this, and the time resolved molecular optical physics hutch. So this is the AMO replacement, if you will. This is hutch number 1 replacement. And I would have to disagree with Mike about the acronyms. Peter gave some fantastic acronyms for the next generation instruments. He's the one person, and he also, and there's another great acronym here coming, and I'll show you. It's fantastic. And I'll give you a little background on it. But so this next generation atomic, molecular, and accelerator science and technology instrument, the NAMASTE instrument. So what this is largely a holdover. This is this instrument right here. This is what our, if you're familiar with LCLS-I operations, this is the LAMP instrument. So this is a multi-purpose instrument that can be fit for charged particle spectroscopy, as well as forward scattering imaging, single particle imaging, condensed phase chemistry. You name it, it's pretty much multiplexable. I mean, it's basically a Swiss Army knife. The focus of that instrument and the target of those techniques are going to be a little down selected and more specialized moving forward for LCLS-II to really ensure that high repetition rate and take full advantage of it. As other components of the total experimental end station, such as forward scattering imaging detectors on single frame at multi-kilohertz, as that technology catches up to us, then we'll start bringing on that technology. But Andy will talk about that type of science in a little bit for TXI. And then the next one is the DREAM end station. So it's another great acronym. Come on. It's Dynamic Reaction Microscope. And so this is what's commonly seen at the University of Kansas State University or University of Connecticut, and on Flash, and also now at the European Expo at the SQS Beamline. This is what is commonly known as a COLTRIMS or coincidence type measurement. And so what you kind of see here is a very, this is this instrument here. These are these Helmholtz coils to negate the magnetic field of the Earth. And so just to walk you kind of through this, I didn't do this a very good job here. So beam is coming from left to right into these are Kirkpatrick Bayes focusing optics to focus to a 1 micron spot, about a 30th the size of the width of your hair. And so we have this NAMASTE end station. These boxes up to the top are where you optically couple in an optical pump. So anywhere from 120 hertz to the multi-kilohertz range, we'll be able to do into these end stations. Series of laser incoupling and differential pumping sections, and then beam diagnostics to help us steer the beam where we need it to be and characterize it and diagnose it. And then we spend that beam as it defocuses. Here's another set of KBs that have a very tremendous fast focus to get to about 300 nanometers into the DREAM end station. So a very, very small focus, high flux. And the super unique characteristic about this is you want to look at single ion coincidences, single electron ion coincidences. And so with that, you need very, 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 very dilute targets, just like Mike was talking about, pushing the envelope of looking at, I want to see what this one molecule does, how this one electron interacts, and so where does it come from that ion? And you want to see, like, I can track this reaction in time and very fast, up to attosecond capabilities. Base pressure with the gas running is 10 to the minus 10 torr. very, 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 very dilute samples. Base pressure is 10 to 11 or so. It's not a lot of molecules in there, so you got to take advantage of this high repetition rate. If you try to do this at 120 hertz, good luck. Time resolve. And so would be very hard signal to noise. And so looking at NAMASTE, one of the things that we want to produce and really tackle as a soft X-ray science, as well as also LCLS-II and LCLS-I, is a pursuit of attosecond science. And so we have recently have some great results from LCLS-I at 120 hertz in the AMO, looking at the angular streaking of attosecond sciences. And so what we have this here, we have this thing called the cookie box. This actually made the cover of Nature Photonics by one of our lead scientists and our senior staff scientist, Ryan Coffey, and his team. And so what we can look at this, look at how on these very, very fast attosecond these pulses, we put a circularly polarized light in there, and we want to streak and track all these chemical reactions and these charged particle times of flight on attosecond time resolved photoelectron spectroscopy. And the nice thing about it is all these different arrays of MCPs. So these are little individually biased and tuned up MCPs. So you can tune some to look at different Auger lifetimes and Auger electrons, or just the different lower energy photoelectrons, just from say valence or from core. So we can look at one shot. We can have a complete read of how this electron's interacting in very fast time. I put this on here. This is not kind of what the spectrum would look like, but this is looking at trying to probe two different edges, say a carbon or an oxygen, or a carbon and a nitrogen. See, because the interesting stuff in chemistry, me being a chemist, is stuff that actually contains carbon, nitrogen, and oxygen. As from AMO physicists, N2 is not really a molecule, but that's just me. So we're going to try to focus on attosecond spectroscopy in both of these end stations, and this is how we will try to diagnose not only the attosecond pulses, but try to do some really fast and fantastic photoelectron spectroscopy. And so here's DREAM. Very, very, very looks complicated. So the beam would be coming, I think it's actually coming from right to left in this case. And so this is this COLTRIMS. So what we have here are two hexadiode, hexaanode detectors coming out in this plane here, normal to the X-ray propagation. So one is charging, looking at the ions produced, and the other is looking at the fast photoelectrons produced. And so when you have this very dilute target in a molecular beam, so we want to look at tracking chemical reactions as they evolve. So basically looking at specific species from a photoion and from a photoelectron. And so high repetition rate is needed. You can kind of see all this stuff. I'm not going to go into specifically this, but the spectrometers are here. Large, in order to have a 5 micron optical beam overlap with a 300 nanometer X-ray beam, it's got to be pretty stable. And so we have solid built, rugged, tough granite stands, KB, and all our optics and laser incoupling are, like monolithically mounted to this thing. So if anything moves, it all moves together. And so we can kind of keep that overlap as well as possible. And so this is kind of what a COLTRIMS experiment would look like. And so we have, inside the spectrometer, so the X-rays are zooming through like this way. And in this case, we have the electrons being detected over here and the ions being detected over here. The reason why you kind of see this thing going loopity-loop, electrons move a lot faster than ions, so we need to slow them down so they can hit at the same time. So you know that they're coincidence into a gate window, so you can see exactly what's going on here. And so we need quite a high electron to ion resolution. We need single photon sensitivity as well. And Mike said, not having just 100 femtoseconds locking here at LCLS-I, this is not good enough. And so we have this a well-rounded plan to get us to this 10 femtosecond. Thankfully, the superconducting LINAC is a much calmer, much more stable system as opposed to our warm copper LINAC friend. And so even though it works great, but have this high synchronization is critical, not only just for this 10 femtosecond business, but moving forward when we get to the attosecond regime. We need that quite well. And so basically we can look at this is acetylene, and this is, sorry, there's two different molecules on there, so I apologize, but looking at how this the electrons and the ions involved in this isomerization of acetylene you can track that chemical reaction in real time, watching this thing move around. Another great technique is hydrogen migration, watching that, and then charge transfer dynamics as well through different edges in this molecule. You can clock this electron as it moves through and then eventually becomes ionized. And I guess I took that out. So yeah, and so basically that was it.
Oh, they are. Sorry. Which one was? No. Okay. Okay. Hi, my name is Georgi Dekovsky, and I'll tell you a thing or two about the NEH 2.2 instrument. So, unlike the other instruments, I'm not really fond of coming up with cute acronyms, so I just kept letters and numbers. So, when people that don't really know what I do ask me, okay, what is your work really? And I say, well, I shine X-rays at samples and I try and see what happens. But they say, but really, what is really that you're trying to do? I go into an explanation that kind of follows this cute cartoon. So if we really want to know about spectroscopy, then we really need to know what is the energy of the X-rays coming in and the energy of the X-rays coming out. If we want to learn how X-rays scattered by the sample, we do diffraction. If we want to know stuff about the position of different kind of atomic species, we do imaging. And we can do all those things and do dynamics. Of course, it will be beneficial if we have a very short X-ray pulses so we can track the fastest processes. So as Mike mentioned earlier, LCLS-II is all about really high resolution measurements. So for me, that means doing spectroscopy and hopefully time resolved spectroscopy really at the fundamental limit, which is, of course, posed by none other by Heisenberg. So we can only do a very fine resolution with a certain time resolution at the same time. So what is the energy range that we want to do this spectroscopy? Well, for me, I'm really concentrating on soft X-rays. So these are X-rays that can tell us really a lot about properties of, for example, biologically relevant samples, such as carbon, nitrogen, and oxygen. And a lot of the 3D transition metals, so these are the transition metal oxides that form some of the very fascinating phenomena that are really at the heart of condensed matter community today. For example, high temperature superconductivity or colossal magnetic resistance or magnetism in general. So in order to study it, to kind of gain access to the relevant kind of absorption edges for these materials, we need to cover the energy range approximately for 250 eV all the way up to 1.2, and for us, 1.6 kiloelectron volts. So when we started designing, of course, the Beamline, we had to have some guiding principles. So this is just a summary slide of what we put down together. Yes, we need to have this energy range. We need to transport the beam to our experimental station with a certain efficiency. We need to have this very high resolving power, 50,000 or so. So the resolving power is really the inverse of the ratio between the photon energy and the energy resolution. So, for example, to have a resolving power of 50,000 at 1 kiloelectron volt means to have an energy resolution of 20 millielectron volts. This is really, really a tiny number. It's a tiny number even if you do spectroscopy in the optical range, and this is many times harder because these are X-rays, so they are much more difficult to control. And of course, we want to have a variable polarization and so forth and control the spot size of the beam. So what are really the techniques of choice for our spectroscopy applications? Well, they're really kind of summarized by X-ray absorption spectroscopy, X-ray emission spectroscopy, and resonant inelastic X-ray scattering. They're all really linked together. If you have a sample, and this can be really any atomic species from the periodic table, you know that they are characterized by these very unique atomic levels that the electrons are sitting at. So if we come in with the X-rays of well-defined energy, we can promote an electron into an occupied state. That's the process of absorption. And by changing the incoming energy, we can see what gets transmitted to the sample, and this gives us the X-ray absorption spectrum. At the same time, if there is a mean to track what is the energy of the photons that come out, the electrons that fill that empty state here, we can get X-ray emission spectroscopy. And this really tells us a lot about the occupied density of states. And in order to do this, we need to have a grading spectrometer. For the soft X-ray regime, this is by far the method of choice, to disperse the beam and send it to a detector and measure each color individually. And resonant inelastic X-ray scattering is really a combination of these two techniques in one, but it's really one unique event that you promote an electron and another electron rapidly falls down. It's essentially a way of doing Raman spectroscopy. So for those of you who have done optical experiments, Chandrasekhar Raman came up with this Raman spectroscopy idea almost 100 years ago, that the color of the light that you shine in your sample can differ than the color of the light that comes out. And this tiny change of energy tells you what is the excitation that you create in your sample. And this is a very, very unique knowledge that is very precise and very good to know if you have X-rays, because you can cue them to a particular absorption edge, and that can tell you a lot about the system of interest. So we're really after this resonant inelastic X-ray scattering technique. So in order to really accommodate a broad scientific community that we're having today, we are sending a dedicated beamline to the second floor of our near experimental hall. And we'll have this large hutch that hopefully will allow us to place a few end stations tailored to specific applications. So the first end station that we're going to have is our RIXS end station that's really targeted solid samples. So in solid samples, these really small energy excitations are very, very low in energy. So we really need to disperse them very, very well. So we need to have a very big spectrometer. So I'll tell you a little bit more about this in a second, but we need to put our detector far away so that we can measure things with a very high resolution. Keep in mind, this RIXS technique is very, very photon hungry. So you measure one photon out of 100 million or so that you put on your sample. So it's really time consuming. And we hope to really change the game with LCLS-II when we have much higher flux. And we also want to have a second end station which will locate somewhere downstream that can essentially do the same technique but on liquid samples. And I'll tell you a little bit more about that in a second. So if you're a biologist or a chemist, some of the most fundamental questions that you might want to answer are, what happens, for example, in photosynthesis? So plants absorb energy from the sun, they absorb light, and somehow electrons go through this convoluted cycle process, and ultimately you get oxygen out that we can breathe and live. So we know a lot about photosynthesis, but we also don't know quite a lot as well. So RIXS can tell us really a lot of detailed information about how this process evolves in time. We can simulate this light absorption by shining an optical laser first. And this is an extremely challenging technique to do today. This set of kind of scans that we can take at different time delays takes 40 or 50 or 60 hours of continuous data accumulation. And this is not really done at the relevant concentration that mimics nature itself. So with the 3 or 4 orders of magnitude higher flux that we project to have to LCLS-II, this will be really telling us a heck of a lot more information. So in order to accommodate these experiments, which are really done in solution, we're designing this liquid jet end station. Again, the focus here is on fluids. So the fluids will come in from an injector from the top, and we'll have a complicated end station that will allow us to both inject those fluids but maintain a reasonable vacuum, because the soft X-rays can be absorbed in air, so everything needs to be kind of at a low pressure. Not as low as Mike was mentioning earlier, but still. And we have a few X-ray emission spectrometer that can tell us really what's the energy coming out. We're actually quite excited about the development of a new type of spectrometer. It's not this grading spectrometer that I mentioned earlier, but it's based on these transition edge sensors, which are really tiny elements. They're about the size of a penny here, but they're really cooled down to a very, very low temperature, and they're superconducting. So if they absorb light, they go into their normal state. So this jump in resistance tells us exactly what their photon energy is. So it's a new technology, it's fastly developing, and we're quite excited to see how it can be applied for our cases. On the other case is RIXS for condensed matter systems, as I mentioned earlier. Really the target is very, very low excitations, and especially those are very interested in complex systems. Those are correlated materials where you have a very strong interaction between electronic, spin, orbital, and lattice degrees of freedom. And here, the name of the game here is what is really going on very kind of at the tens of MeV energy scale, because we have competing kind of electronic ground states that can be pushed one way or the other by engineering different materials. And the global functional properties of different materials are really governed by these low energy excitations. So again, we're projecting to have a flux some 3 or 4 orders of magnitude higher than what people are used to at synchrotrons today. And for us to be able to take this spectrum and to take them at different time delays so we can do pump-pro spectroscopy is something that will change the game. So this is the end station, that the way it's going to look hopefully in about 3 or so years in the future. This will be the target place that we put our sample. All the samples usually have to be cooled down because the interesting physics happens at low temperature. We have a grading spectrometer that can travel around this long arc that's about 6 meters long, and the detector here can capture the dispersed beam. And really want to measure the spectrum as a function of angle, because this is of particular importance in correlated systems. And I'll finish with this last slide here. Turns out that we're at SLAC here have done something like this more than 50 years ago. Of course, we were not using X-rays at the time. At this time, SLAC was really a facility aimed at high energy physics, but this is a human being here at this 30-meter long spectrometer arm that was measuring some elementary particles that are being scattered, and it weighed 500 tons. It's a phenomenal device that doesn't exist today, but this end station A is still in existence. And as I like to say, we're standing on the shoulders of giants here. So we've done this before. We're pretty confident we can do it again, and for a new application. Thank you for your attention.
Yes. Yeah. So, thank you. My name's Andy. I'm here to talk about the Tender X-ray instrument, or TXI. It operates in the Tender X-ray range. For those who don't know, the Tender X-ray range goes from about the K-edge of silicon to the K-edge of iron, so about 1.5 keV to about 7 keV. Currently, we're slightly blind there. No instrument right now at LCLS operates above 2 keV, between 2 keV and 5 keV. So that is one of the issues we want to address. The second one is we really want a place where we could combine the two undulators. And yes, we are going to cross the streams, and really want to do this because there's no one else in the world that this is even capable to do this. So what we want, this is a really simple cartoon. I kind of stripped away everything except the most important facts here for you to take away. We're going to go from about 200 eV to 5 keV on the soft X-ray branch line, and we can go from about 1 keV to 7 on the hard, maybe up to 10, depending on optical coatings. We're trying to go from a delay of up to a nanosecond, and we have some offset mirrors, and we have a pair of Kirkpatrick-Baez mirrors to focus the beams. And we are planning on a focal diameter of about 1 micron, and we can expand the beam up to 10 microns for some experiments. We are planning a lot of aerosols and liquid samples for obvious reasons, that this is high power. You're talking about 200 watts of X-rays. They tend to melt through metals. And we're also talking about a forward scattering detector and additional spectrometers to do photo emission. Not shown is a crystal delay line. This will be on the hard X-ray branch line, so we can actually not only do we, because currently we have to do X-ray pump, X-ray probe, we have 2 accelerators, a superconducting accelerator and the copper LINAC, and if you want to synchronize those two and overlap them, you're limited to 120 hertz. But if the cross sections are good, and for some experiments you want to go above this to get a better signal noise, you can double pump the photocathode on the superconducting accelerator and use a fast kicker to separate the two bunches, but then you have to delay one by about 5.4 nanoseconds, or about 7 feet of delay. Which, to do this, we'll use crystals, and then we can synchronize and actually operate this up to 10 kilohertz. So I wanted to go over some of the possible science cases. As I said, the biggest thing is we're probably the only place in the world where you can do nonlinear X-ray pump, X-ray probe experiments. I've kind of broken down into the stuff you would do with the lasers, the stuff you would do if you're looking at, like, for example, Bragg peaks and you want to pump with the FEL and then probe with a hard X-ray beam. So you can think of matter under extreme conditions. You can think of Fourier transform inelastic X-ray scattering, to look at photon dynamics, to look at plasmas. And you can think of coincidence like catalysts, where you want to get with high resolution imaging from scatter, but you also want to get very high resolution spectroscopy at the soft X-rays of carbon, oxygen, and nitrogen. You can also think, as I said, we are the only instrument that is going to be in the tender range for forward scattering. So you can think of fluctuation sacks, single particle imaging. I'll explain those a little more. I'll explain most of these more. And you can also think of tender spectroscopy, something it's hard for us to do. So for the parameters, I said, this is probably the most important table for you guys. We'll be operating on the soft X-ray side from 1.2 kV to 5, and the hard from about 1 to 10. We can go a little bit outside this range, which we're trying. Now the catch is we can't do this entire range at once with a superconducting accelerator, just because you can't. You have to use the superconductor. There's a lot of technical reasons about having how much GeV, 4 GeV coming out of the superconducting accelerator, and what that means for the undulator K parameters. Hence why this table has different numbers of what's possible for overlaps. Photon size, we are planning our optics, if they're ideal and perfect, to get about a 700 nanometer by 930 nanometer spot, if they're ideal and perfect, but nothing is in the life. So we're expecting to be about 1 micron by 1 micron. And we're trying to keep the overlap within 10% of the beam, or about 100 nanometers. And that's quite challenging. We also want to synchronize to about 10 femtoseconds, if not better, because if you're looking at electron transitions, and right now, laser pump, laser probe experiments are looking at phonons. They're looking at longer things in the femtosecond, 10 femtosecond range. We're looking at atoms vibrating and bouncing around. We're looking at electrons and atoms, and electrons and molecules, and how these molecular orbitals change. And those are in the tens, few femtoseconds to tens of femtoseconds, even sometimes in the hundreds of attosecond range. So I'm just trying to give you some ideas of what you can do. And one of them, you've heard Georgi just talk about RIXS. We can simulate that. We can actually send a simulated signal. So the idea is, if you come in with a photon and you have a seed photon, you can actually, that matches the energy loss, you can actually get a gain signal out. This is in laser technology called CARS spectroscopy, Coherent anti-Stokes Raman spectroscopy. So you pump a signal, you have a second pulse that drives a transition, so you separate these by the transition, and you probe. So one idea is, why would you want to do this? Why would you want to do this when we can already probe 280 eV photons and carbon? Well, the problem is with most materials at 280 eV, your penetration depth is tens of nanometers, and if you have a sample that's microns thick, you're not going to see anything. So the idea is to come in with harder photon energies with more penetration and do these processes to simulate the signal so we can see it. So imagine having a flame, and you want to see a three-dimensional, how a flame moves in 3 dimensions, or as a function of Z from the source. You can think of looking at the CO, methane, CO2, and trace all these elements as a function of Z position. And if you're looking at a solid, you can think about tracing them as a function. You can rotate the sample as a function of 3D tomography with a 1 micron or sub-micron resolution. And that would be kind of cool. So if you, so I said, you're coming in with a pump probe. If you want to do the math, for example, I just chose 1.3 and 1.6 keV because until high HE, this is something we can do with superconductor on both sides. Or if we're, you can actually do this. Not only that, but the cool thing is the CARS signal is because we're coming in with about 100 milliradian or 5-degree separation crossing of these two beams. This signal is completely independent. There's no background, so this signal should be very easy to see. As I said, you can think of two photons. You can think of some nonlinear MEC type experiments. You can think of multicoral spectroscopy. Thinking of like the titanium has a K edge at 4.9, oxygen has a K edge at 530 eV, and also titanium has a L edge at, I believe it's 560 eV. So you can come in with those three wave photon energies and kick out different core holes, or make different core holes, and probe how the electrons interact with each other. These are things that I want you to think about when you're designing experiments. This has never been done, and the field's pretty well wide open. Other ideas, as I said, you can think of matter under extreme conditions. We can tailor the absorption and the power to probe very extreme cases of matter. Or you can actually pluck the system very specifically. And if you're looking at just off Bragg peaks, we've done this with laser pump X-ray probe, you can actually see phonons. And you get really high resolution cases of actually looking at how energy transfers through a crystal. And these are some also interesting science cases we're thinking about looking at. As a course, I can't just stop with the two beams, but we are in the tender range. And for biological imaging soot particles, pretty much imaging where you want to get sub-nanometer resolution or angstrom resolution, you really need to be about 2.5 to 3 keV to get angstrom resolution. Why is this? Well, you're doing forward scattering. And there are no really good optics for collecting high resolution scattered signals. So we just put a detector there, and if you have a coherent beam, you can actually retrace the object or figure out what the object is. For example, this case, this is a rice dwarf virus. Diffraction pattern is a 70 nanometer virus, and you can see the fringes. And if you think of where you see these spikes of fringes, you can tell from this picture that's icosahedron, right? And if you collect enough data from these things, you can actually put them into a three-dimensional slice of voxels and actually reconstruct the object. And in this case, we've gotten this down to below 10 nanometer resolution, and we're pushing it in the few fives of nanometers. Problem is, pushing it further is rather hard because for this to get a 10 nanometer resolution, it took about 3,000 images. To get 1 nanometer resolution, it's going to take about 30 to 50,000 images. And to get angstrom resolution, it's going to take hundreds of thousands of images. And at 120 hertz beam, it may sound like a lot, but you have a 1% hit rates because these are very dilute samples. You do not want clusters of these things. And that means you're down in the week-long period to get a few nanometer resolutions. If you want to get into the angstrom regime, you need to have high repetition rate. Another idea is, well, how about we do SACs, but with a dilute sample, and collect the, in traditional SACs, you're just getting radial averages. But if you look at the single-shot nature of our beam, we can actually see non-radial components. And if we take those non-radial components of, let's say, 3 to 10 objects in the beam, we can actually use that correlation data to refine structural models. So it's kind of like SACs on steroids, or fluctuation of SACs, as we call it. And we can actually see certain dynamics. You can think of mixing substrates into this, or mixing chemicals to actually see vibration, see changes in protein structure without crystallization and in a liquid jet. This is all possible, and as I said, you really want to be at the whatever resolution you want to be at that photon with a corresponding photon energy and collect a 60-degree diffraction pattern. Other approaches we're planning on doing are mostly spectroscopy, absorption, and emission. Photo emission will be from the start. Absorption will have to wait until we get a delay line, mostly because for absorption spectroscopy, you really want a monochromatic beam, and we're designing the beam to be as bright as possible, which means we want to use a full spectrum. With that, I want to bring up the timeline again. Mike showed this at the beginning, and try to answer any of your questions. Thank you very much. Yes? What do you mean by USACs? Probably. You'd have to, if you want to do that, you'd probably have to go to XES, one of the other instruments that Mangle will be talking about. The reason is our hutch is limited in space. When we have a meter-long KBs to collect a full beam, the focal length, the focus position is right in the center of which means we have 3 meters of space left downstream. And with the detector and electronics, I cannot get a detector further than about 1.5 meters realistically before I need to put other pieces of equipment. So 1.5 meters is about where you're going to collect your lowest Q data. A pixel size is 75 microns to 100 microns for the EPICs we're planning on using. So based on that, you can probably calculate what what you need for ultra low Sachs.
Oh, great. Is it here? Mine is a different talk. Great. Hi, my name is May, and I will be talking mainly about the hard X-ray instruments, which, unlike a little bit of the LCLS-II, they exist, and although they may change someday with the LCLS-II HE upgrade, more acronyms again, I'm currently going to be talking about what the current capabilities are and how to write a good proposal to take advantage of the various capabilities. So the instruments that I'll be talking about are XPP, XCS, MFX, and CXI. So they are here, the green hutch, XPP, which is the last hutch in the New Experimental Hall. And then after the XRT, the X-ray transport tunnel, it's XCS, MFX, CXI, which are the X-ray correlation spectroscopy, macromolecular femtosecond crystallography, and the coherent X-ray imaging beamlines. So these four instruments, because there are four, there's a really large array of science capabilities. And so I will just talk briefly about what the general capabilities are, so the kind of the standard hardware that you can expect in all of them, and then I'll go into a little bit more specific capabilities for each of the individual end stations. So, whoops, sorry. So the hard X-ray energies are 5 to 10 keV. We can quibble about the low end and the high end, but I would say 90% of our experiments are done with these energies. There are focusing capabilities, CRLs, at all of the end stations, and there are KB mirrors at CXI that can focus the beam down to 1 micron or 100 nanometers. There are lasers for pump probe experiments at all of them. Along with the laser for pump probe, there's femtosecond timing capabilities. Because the SASI beam certainly jitters and timing-wise, so it's plus or minus 100 femtoseconds because of the the SASI, the spontaneous emission capabilities. We really need femtosecond timing capabilities to see exactly what the time delay is between your optical laser and your X-ray pulse, which is coming in. And so that is available for all of them. We have monochromatic beam capabilities at XPP and XCS. And then pink SASI beam, which is the standard LCLS beam, is available at all of them. We have a set of spectrometers, which can be incorporated into almost any of the instruments, any of the sample environments. So if you want to do spectroscopy as a part of another type of experiment, that's very, we're very flexible with that. And one of the things that is very special to the hard X-ray department is that we can do a lot of multiplexing. Multiplexing, what this does is it increases the amount of beam time we have because we can run more than one instrument at a time. And so whenever we are operating in a monochromatic mode, what the monochromator does is it takes out a single slice, a single energy slice of the SASI beam, and then the rest of the SASI beam can be used by one of the next instruments. So whenever that happens, we can double the amount of beam time we have, which is very good because, as Mike said, we are not, we're a little bit short on beam time. So one thing that's something that we can do to help. So I will also briefly talk about the X-ray detectors that we have. There's lots of X-ray of detectors available, but only a few of them are really suitable for FEL science. So usually what the capabilities we need are the high repetition rate. And so most, a lot of your a lot of your CCDs do not operate at the 120 hertz rate that can really take advantage of our repetition rate. And so in that end, we have they're specially developed detectors that were built for us, such as the CS pad. This is a 2.3 megapixel detector, which can run at 120 hertz. It has single photon sensitivity, which means it can detect a single photon as well as a reasonable dynamic range, which means it can detect several hundreds maybe even thousands of photons, depending on the photon energy. There are rayonics, this is a scintillation detector, which can run at 30 hertz. But is also very good if you need really high dynamic range. So if you anticipate very, very strong signals, like a Bragg peak, a very intense Bragg peaks, this is the detector that you would use for that. There's also a series of kind of smaller detectors. The CS pad 140K, which is a 1 2x2 of the full CS pad. And also the EPIX 100, which can be used as small detectors to be used for spectroscopy, or to be used if you want to go high angle and you have some high angle scattering you want to see. All of these three are relatively low noise, which is very important if you have very low signal, which a lot of spectroscopy signals are very low. Most of these detectors can be incorporated at any of the instruments. You just have to figure out what geometry you want and what science case you actually need, but those things are typically readily available anywhere. Another thing that we have to think about is sample delivery, because it's 120 hertz. You want to put in a sample quickly. You want to replenish your sample quickly if you are working in the diffract and destroy regime. So diffract and destroy, you've probably heard this word quite a lot. We have a very intense X-ray beam, and so typically many samples are destroyed using a single pulse. And so if you're going to do 120 hertz repetition rate, that means you need to replenish your sample at 120 hertz. So for this, many sample delivery techniques and technologies were developed. And so we'll talk about, you've probably heard the term liquid jets quite a lot. Liquid jets actually incorporate a whole variety of jets, all with different capabilities. And so kind of the bread and butter that we use is the gas dynamic virtual nozzle, which is here. What this is a nozzle that creates about a 1 micron liquid jet, in which case you can suspend your sample, be it a protein crystal or a salt or whatever single particle that you want. And then using this high pressure helium sheath flow focusing, you can focus down to this 1 micron jet. It goes at very, very high speeds, around 10 meters per second. And so you can easily match the 120 hertz rep rate that you need. For other samples, which perhaps do not like the liquid that is here, or if you have a protein crystal that does not like water or whatever buffer that is there, there's a lapidic cubic phase jet, which is typically a slow-moving jet that is typically very viscous, and you can, if your sample is more amenable to that kind of material or that kind of solution, you can use that. There's the electro-spinning jet, which uses kind of electrospray technology to create a liquid jet which is even smaller than the standard GDVN. The electro-spinning jet is very, very good because it moves, the jet is so much smaller. It is much better in terms of sample consumption. So if you have a very, very precious sample that you don't want to be gone in, within half an hour, you should think about using a mesh jet. There's the double flow focusing jet, which is also a very low flow kind of jet technology that has two concentric liquid jets, one inner, one outer. And then what the outer flow does is that it kind of squeezes the inner jet to become even smaller. And because of that, you can have very low sample consumption, because you don't need to have the huge amounts of sample in order for it to flow focus using this helium. You have an additional outside jet that helps with the focusing. There's Rayleigh jets, which are very big jets. There are liquid sheet jets, which can be very broad, which is what it sounds like, a liquid sheet, about 10 microns in thickness if you wanted to do liquid scattering experiments. And then a new kind of technology that's been built that's very exciting is also mixing jets. Mixing jets are jets where you actually have two inlets. And so they actually have mixing, kind of like a mixing compartment using various, there's a couple of different techniques which mix upstream within the jet itself. So if you want to do stuff that involves dynamics, or mixing dynamics where two things are reacting, and you want to study that kind of process in time, mixing jets are a new and exciting capability for studying these kinds of dynamics within this liquid jet kind of paradigm. There's also this aerodynamic lens stack, which is used very often for single particle imaging. What this is that what it does is it focuses aerosols. So if you want to have like a solution of, say, particles or viruses, what you can do is you can aerosolize them. And then what the aerodynamic lens stack has is a series of pores which slowly focus the aerosol into a very, very small spot. And so for that, because your hit rate, you want it to be very, very dense so you can have a lot of data. And if you have a very diffuse aerosol, you will never get that kind of density that you need. So this aerodynamic lens stack is used in order to focus down your aerosol. Okay, so those are kind of the general capabilities at all of them. And now I'll go into a little bit specific. The first instrument is the XPP, X-ray pump probe instrument. And as you can possibly imagine, typically optical pump X-ray probe experiments are done here. It is a very versatile instrument. It is at ambient pressure, and it can support a wide variety of sample environments. So there's a three-circle goniometer, a kappa diffractometer. There can be a vacuum chamber installed if you need to do vacuum experiments. There's a liquid helium enclosure for liquid jets. And then you can also do cryo experiments down to 100K. The XPP experiment is typically used in monochromatic mode. There's an LODCM, which is a large offset double crystal monochromator. That's 2 silicon 111 crystals. And so you have very good monochromaticity, delta E over E, about 1 × 10⁻⁴. So that means about 1 electron volt, a few electron volt bandwidth. And then the techniques that you can use at XPP are a wide variety: diffraction, fluorescence, scattering, spectroscopy, any number of techniques. And so if it's one of those, if you have a very new, interesting, fancy, crazy experiment that needs 10 detectors and a whole bunch of sample delivery, XPP is typically a good place to go for that. So I will show one of these kind of crazy experiments that was done kind of recently. And this is electron-phonon coupling in iron selenide using terahertz pump, diffraction, and time-resolved angled RPES. So this is what this was it's a terahertz pump, X-ray, and UV probe. So it's pump probe experiment. And so the science case which they were looking at was that iron selenide is an iron-based superconductor, which people don't really understand why iron-based superconductors actually conduct. This is part of these systems, kind of like the Coop rates, where people are like, we see superconductivity, we don't really know exactly why. It's not really described by standard, BCS theory or anything. And so these people were thinking that by doing diffraction, which looks at how the lattice vibrates, so these are phonon modes, and how that couples with the electron, the electron energy states, perhaps that can tell us something about why these are superconducting. And so what they found was that if you excite it with a terahertz pump, and what this does is that it excites the selenium atoms, and so they kind of vibrate, creating this phonon mode. And then if you probe what the electron band structure is with this time-resolved resolved photoemission spectroscopy, RPES is just easier. RPES, what RPES does is doesn't just look at the electron energies, but it also looks at the energy, the electron momentum. Then you can try to see if there's kind of this electron-phonon coupling that helps to amplify the effect which you see, which can lead to superconductivity. So what they did here is that they hit it with this terahertz pump, and then you can see the ringing of the lattice. And so this is the selenium atoms going back and forth. And then what they also did at the same time is that they used this kind of 60 EV UV probe in order to do RPES, to look at what the electron momentums were and energies. And what they found is that there's very much this correlation between the lattice vibration and the phonon mode, and the electron energy states. And so this kind of proves, or it shows evidence that there is this kind of electron-phonon coupling, which kind of enhances the energy states, which can lead to these kind of exotic effects. And so that's one example of kind of a very intense pump probe experiment. The next instrument is the X-ray correlation spectroscopy XCS instrument. This is the purple hutch and the first one in the far experimental hall. This hutch has a very long 8-meter detector arm and is the natural home for X-ray coherent speckle techniques. And so I'll explain a little bit what that is. So coherent techniques involve X-ray photon correlation spectroscopy, XPCS, and its kind of sister cousin XSVS, which is X-ray speckle visibility spectroscopy. It also is a good place to do Bragg coherent diffractive imaging because you have that long detector arm that can swing out to very high angles. So if you have a Bragg peak, which you want to kind of track and see what the coherent, the CDI imaging looks like, this is a good place to actually do that. And so one of the things which they do here is they look at equilibrium dynamics. So equilibrium dynamics are typically very hard to actually see because they are by their nature fairly small. And so one thing that they can do with XPCS, which perhaps I should explain briefly what that is. XPCS is when you take coherent speckle images of an ensemble of particles and you take it at various time delays. And by looking at how the speckle evolves in time, you can have a feeling for what the dynamics are. So for example, if you have a series of colloids and you can take speckle patterns at delta t over a long period of time, you can see how the diffusion works. So you can study, for example, Brownian motion. The kind of new version, the new FEL version of that is XSVS. And what this is that instead of taking snapshots at delta t, at various time delays, what you do is, in order to get very, very short dynamic like time scales, you don't have a detector that can run that fast. So let's say you want to study femtosecond or nanosecond dynamics. You don't have a detector that can distinguish between two pulses which are nanoseconds apart. And so what you have to do there is you have to use a different technique, which is what you do is you kind of look at how the speckle contrast decreases with either two pulses, which are nanoseconds apart, or with a single pulse that is a certain amount of time long. So let's say if you have dynamics on the time scale of 100 femtoseconds, that means if you use a 1 or 10 femtosecond pulse, your speckle contrast should be sharper than if you used a 100 femtosecond pulse, because your system is evolving within those 100 femtoseconds, and so because of that, you would have this blurring out in the speckle contrast. So this is what they did here. So they used XSVS to study caging dynamics in water with different pulse lengths. And so what they did here was that they used the native kind of variation in pulse duration that you can get from the LCLS machine. So the LCLS machine can provide pulse durations from about 10 femtoseconds or less up to hundreds of femtoseconds. And so if you want to study dynamics at that time scale, you call the machine and you say, hey, can you please tune to a short pulse, a short pulse length? And so they will tune to that, and you take data using that short pulse length and then have them tune to longer and longer pulse lengths. And you see how the contrast in your speckle pattern washes out with those longer pulse lengths. And that will give you some idea of whether or not you have dynamics during that time. So what they saw here was that they were looking at water. And so water, if you think about the classical Brownian motion picture, it has a ballistic regime, and then it has a diffusive regime. And so typically you see a smooth transition between those two. But what they actually saw was they saw this intermediate regime that was not ballistic and not diffusive, which they, through theory, can explain with a caging mechanism in water. So that means the hydrogen bonds in water actually create this kind of cage that inhibits this kind of ballistic motion of these water particles. And so they were able to do that, and they saw that this existed over the sub 100 femtosecond time scale, which is kind of a very new result that I think people had not thought about before. And so this this experiment, this XSVS with the native LCLS pulse duration is good for kind of less than 200 femtoseconds, which is the kind of the pulse lengths which the LCLS can tune to. If you want to go to longer timescales, however, we do not provide nanosecond pulses. And so what they were able to do at XCS was to develop a split and delay mechanism, which allows you to do XSVS with 2 pulses. And so those 2 pulses are created when one pulse goes in, it is split. One of the pulses is delayed in time, and so that time delay can go from hundreds of femtoseconds to nanoseconds. And so you can do femtosecond, picosecond, and nanosecond dynamics. And then what you do is you delay or like one of them, and then you do the same thing where you look at how the visibility of this speckle decreases as you change the time delay between these 2 pulses. So this split and delay was kind of commissioned about kind of last year, late last year, and this year. And so this is something that is kind of a new capability that we're excited to offer people going forward. Okay. The next, the third hard X-ray instrument is the MFX, which is macromolecular femtosecond crystallography experiment. This is where a lot of serial femtosecond crystallography is done. This instrument has a biological focus. It is also in ambient pressure, and it has a variety of sample environments that can be used to study samples in whatever kind of mechanism or buffer that you want. There's a fast scanning of fixed target samples. So if you have a sample that is very precious and you don't want to suspend it in a liquid jet, then you can deposit them on fixed target samples. You can do 120 hertz fast scanning. This is a piece of hardware that was built by the Center for Free Electron Laser Science, CFEL, in Hamburg. And so what this can do is it's good for very rare and precious samples, and that can get you, that you don't want to put into a liquid jet. If you do have a lot of sample, then you can use the helium-rich ambient, which is the HERA environment, which is just a helium environment that was built by the Max Planck Institute for Medical Research. There's also, if you have a single crystal that's a fixed target that you want to use with a standard goniometer setup, you can use the SSRL SMB goniometer. There's a goniometer, a sample exchange robot for taking kind of like bigger macromolecular crystals. There's also acoustic droplet injection, which is a drop-on-demand tape deck kind of device, which can also which is also good if you have kind of rare samples that you can't perhaps make enough to use a liquid jet for. The fourth, sorry, there's so many. Sorry, there's just so many. The fourth instrument is the Coherent X-ray imaging instrument, which is the CXI. CXI is very special because it is the only hard X-ray instrument that has KB focusing optics. So what this can do is that you can get the highest power density that exists at LCLS is available at this instrument. It has fixed curvature achromatic KB mirrors. There are 3 sample chambers. One is the 1 micron focus using the 1 micron KB mirrors. There's the 100 nanometer focus using those KB mirrors. This provides the highest power density that kind of exists at LCLS. There's, in addition, a parasitic serial sample chamber, which is after the 1 micron focus, so that this the undiffracted beam can be used to do a parasitic experiment afterwards. This also increases the amount of beam time that we can offer. And the main types of experiments that are done at CXI are liquid-jetic experiments and fixed target fast scanning. This is a kind of a new hardware setup, Roadrunner 4, which can be used in the 100 nanometer focus to do 120 hertz fixed target scanning. So one of the very special things I talk about is the high power density. And because of that, you can do a lot of experiments such as nonlinear X-ray experiments. So this was an experiment that really can only be done at CXI in the 100 nanometer focus, where these people did stimulated X-ray emission from manganese complexes in a liquid jet. And so what this means is that stimulated emission, you could probably think that's actually a laser term, which it is. And so what they did is, because of the very high power density, they were able to see a kind of population inversion that you would get. And so what happens is that you have this very intense laser beam coming in. And so what this typically causes is it causes stimulated like a emission. But because of the very high power, what you get is you get more excited states than you do ground states. And what this does is that as this particle gets excited, it actually emits photons, which in turn kind of amplify as it continues along in this jet. And so at some point, they actually see saturation, which means that they are no longer able to excite any more particles because all of the particles have been excited past what they can already handle. That means all of these electrons have already been, put into excited states. There are actually no more core hole electrons available, and so this is actually what happens in a laser. So what they did is they used the SASI laser to create an X-ray laser using using this very high power density. Okay, and so beyond those, so these are kind of specific experiments native to each of the instruments. There's also kind of experiments that we very commonly use. One is this serial femtosecond crystallography, SFX, which you heard about, I think, yesterday. I think Hassan talked about this. And so SFX is a type of protein crystallography where small crystals, which cannot be studied at third-generation sources, are injected into this beam using one of these liquid jets. And many thousands of single diffraction images are obtained. They are merged using this Monte Carlo method. And they can be, so we can determine the structure of very, very small crystals, which cannot be grown to larger size. But more excitingly, we can also study ultrafast dynamics. And so what this means is that if you were to want to excite one of these crystals, right, and let's say you can pump it with an X-ray, with an optical laser, and see some kind of change. But the smaller crystals, which they really do give you an advantage, is that you can actually excite the entire crystal. If you have a very, very huge crystal, you have certainly regions which are excited, which are very excited, but then because the optical laser is attenuated throughout this crystal, you cannot get a very high percentage necessarily of excited states. And so these small crystals are extremely important for studying these ultrafast dynamics. Same thing with mixing. If you want to mix, two things together, let's say you have a protein like crystal, and then you can mix some kind of substrate in to create some kind of reaction. The smaller the crystal it is, the more it is able to penetrate into this crystal, which means you have a higher percentage of excited states, which means you can get much better data than you can from a macro crystal. So this is where SFX really shines. And so this is kind of where the future of protein crystallography is going at LCLS. Another area, which kind of Andy touched on a bit, is single particle imaging and Bragg CDI. So Andy talked about single particle imaging, so I'm not going to go there. But Bragg CDI is the Bragg version of that, where instead of looking at the specular beam, you would look at a Bragg reflection. And because your particle is small and because your beam is very coherent, you can actually see this kind of diffraction pattern, which is the kind of this extended diffraction pattern at every single Bragg peak. And so by doing this, you can use these kind of iterative phase retrieval algorithms. I think Ian McNulty will actually talk about that later. So maybe it'll make more sense when he explains it. And you can actually get a real space reconstruction of the electron density by doing these phase retrieval methods. And so what an experiment which they did here at XPP, but which can probably be done at XCS or maybe even MFX, is that they took this nanoparticle and they were able to hit it with an optical pulse. And so what they were able to do is to excite these acoustic and acoustic phonon mode. And what they could do is that they could actually do a reconstruction of the particle at all of these different time delays, and to see how the strain and the beating of the acoustic phonon mode exists within this particle. And so this is an example of how using the coherence and using kind of the flexible capabilities of the hard X-ray instruments, you could do experiments like these. So I think in the interest of time, I will stop there.
So my name is Bob Nagler. I'm a scientist at the last end station in the row at LCLS, the matter in extreme conditioned end station. I'll give you a short overview of what the instrument can do. Tomorrow there will actually be a much more significant talk of Hej Ali, a colleague of mine, who will touch more on the science. I'll give you a little bit of an introduction. So we do what we call matter in extreme conditions, and extreme in the sense of temperature and density. Now, what's extreme is, of course, very relative. We call it extreme when it's extreme compared to the situation you find on the surface of the Earth. But you don't actually have to go very far to get very, very different conditions. For example, if you go into the Earth, you dig deeper and deeper, you get to pressures and temperatures which are quite high. At the center of the Earth, you have pressures which are millions of atmospheres, so up to 300 GPAs, and temperatures of about 1,000 Kelvin. Sorry, 10,000, roughly around 10,000 Kelvin. So very, very different what you find on the surface. And what actually happens at those densities and temperatures is not quite known. There's still quite some speculation about the state of the matter. We know the core of the Earth is an iron nickel core, but what the exact, it's not liquid, it's a solid core, but what the exact crystallographic state is not completely certain. So if you look at other areas of interest, in a phase diagram of density, or which corresponds to sort of pressure and temperature, we kind of situate in this top right corner here. So we don't do too much of standard plasma physics, which is at high temperature but fairly low densities. But so even magnetic fusion experiments, we don't really do too much. But we are interested in inertial confinement fusion, the stuff that happens inside stellar interiors. Strongly coupled plasmas, so plasmas that are very, very dense, where you have specific phenomena which you don't typically see elsewhere. Warm dense matter is an area we do, and other stellar objects such as accretion disks, white dwarf stars, and cores of larger planets such as Jupiter. For example, if you take Jupiter as an example, it's a gas giant. I always find this very intriguing things. If you descend from outer space into Jupiter, you first start to encounter an atmosphere which is mainly hydrogen. You keep on going deeper and deeper, and the density keeps increasing linearly, but you never actually reach the surface. These planets don't have a surface. You go deeper and deeper. At one point, you are at density you would call this really a liquid, but you never really transfers from a gas phase to a liquid phase. It's a continuous transition. And what the state of this liquid is at pressures up to terapascals, even at the center, is unknown. There's a lot of theory. There's metallic states of hydrogen in these planets which are theorized, but very few experiments, and they're very difficult to do. There's more cataclysmic events, like when large asteroids hit, hits planets or even two planets collide, they cause tremendous shock waves to go into these planets, and they can also change the state of the matter you find there. For example, on Earth, if you go and look at craters where there have been asteroids impacts, you find certain minerals which you don't find anywhere else, and they were really created by the pressure, and they survived, they were stable afterwards. So this is sort of, in broad strokes, what we are interested in studying at MEC, and we don't do this by going out into space or pointing telescopes, but we try to recreate these states into our lab in a vacuum chamber. Now that's difficult, because obviously if you create a piece of a very small sample at these high pressures, it doesn't live very long. It starts to very quickly explode, and you have to investigate it before that happens. And that's where LCLS comes in. So at LCLS, we have this really bright X-ray source, and it's extremely short. So it beats any hydrodynamic expansion, even many of the very fast processes that happen in these materials. So you can create the matter. Generally, we use drive lasers, very strong lasers, and then probe it with LCLS before the changes happen and before the sample has exploded, expanded, and become more dilute. So for LCLS, we need the very short pulses to these experiments. We need the high photon numbers. A lot of the probes we use, they're fairly photon hungry. Sometimes we even just use LCLS itself to create this material. So if you focus our beam to very small spot sizes, we can create temperatures which are high enough to be in these regimes. But most of our experiments use other lasers, drive lasers that create either the high temperatures or the high pressures by heating it or by driving shock waves or using relativistic particles we create to get us into this regime. And then LCLS at MEC, it's a hard X-ray instrument, so we use X-rays from about 4 keV to 12 keV mostly. Most of our experiments are around 8 and above to probe what happened in these materials. And it is really, this short, very bright source has really revolutionized this field and opened up a lot of areas for experimentation. So this is an overview of our hutch, a nice CAD drawing. So we have a big vacuum chamber where all our experiments take place. The X-rays, they come in through this X-ray tube. There's some X-ray diagnostics to qualify them. We have a couple of optical diagnostics on the outside that are used to measure the strength of shock waves and the motion of surfaces of materials. But most of our diagnostics actually sit in this big experimental chamber, which has it's a vacuum chamber with a diameter of 2 meters. Now, when users come in, it's a bit different than most of the other stations at LCLS. This vacuum chamber is generally empty. There's just a sample stage in the middle. Users come in, they put in drive beams, they route their optical lasers to the sample, they put all their diagnostics around it, and they essentially place the diagnostics they want. We have some stock diagnostics which they can use, and they're very frequently used, but sometimes they come with their own spectrometers to look at scattering, X-ray emission, or optical emission from the sample they create, and put that in there. So whatever fits within reason, we can place in this chamber and do an experiment about. So here, as an example, you see 2 X-ray scattering spectrometers, which are used to look at mostly elastic scattering and mostly inelastic scattering, I should say, from the samples we create with our optical lasers. So the 2 optical laser systems we have, so in our hutch we have these big optical enclosures with 2 laser systems, a very short pulse laser system and a more energetic, longer pulse system. So the short pulse system is a fairly standard titanium sapphire laser system with pulse length of around 50 femtoseconds and a total energy of 1 joule. So this gets us to about 200 terawatts. It runs at 5 hertz, and it has a deformable mirror, so the spot sizes you can create are fairly close to diffraction, limited typically with a Strel ratio of about 0.7, 0.8. There's upgrades for this plant to go to much higher energies, but right now this is what's readily available for users. The second system is our nanosecond laser system. So this is a high energy system. We have 2 arms that go into the chamber, which both have 30 joules of energy. The pulse length is about 10 nanoseconds. it can be tailored, so we can make it smaller up to 2 to 20 nanoseconds. We can put specific shapes in that temporal profile to ramp it to get other shock profiles. And it's generally used with fairly big spots of about 100 to 250 micron and used to drive shock waves into materials. So you drive a shock wave, goes to very high pressures, and then you probe the state you've created with the X-rays. It's a fairly slow system, so it only can produce one shot every 7 minutes at full power. So you have to keep that in mind. So this is a bit of a teaser. Oops. I'll go back here. So, okay. So, okay. So this is, I'll just give you one teaser where we combined like both an imaging technique and an X-ray technique. So many of the diagnostics you've seen in the other hard X-ray instruments, they work here. And so this is, for example, an imaging technique we used where we looked at a shock wave as it propagates through a sample. So here you have a silicon wafer which has a thickness of about 100 micron, and the X-rays go like perpendicular to the screen here. And on the top, the edge of this wafer, we shoot our optical laser. And so what happens is a shock wave will propagate through this sample, and we take, with the X-rays, we take snapshots about every nanosecond. So as you see, the shock wave develops. I'll stop it here for a second. So it propagates from the center, it pushes the material around, and before the shock wave, you see this very dense region where more of the X-rays have been absorbed. And so you can get information about the density of the shock wave you created, obviously the speed, the velocity of the shock wave you get, and you see this other strange feature here, which is actually a linear precursor of the shock, which you can see. So with this technique, you actually can image directly on a fairly macroscopic scale what happens when you shoot such a laser. So the total field of view here is 300 micron. Now you can combine this with X-ray diffraction, which we've also done. So this is sort of one of these images you saw before, but rotated 90 degrees. And since we have X-rays, we can focus these X-rays to different regions in the shock profile and see what state of matter we've created. So initially, before everything, you see, for example, there's not much going on. There's not really any bi-sharing, so which is normal because we use a single crystal silicon here. And if you probe behind the second shock wave, you see diffraction peaks. So the bi-sharings appear that tell you that a phase transition has happened to a shock state of silicon. And by evaluating these, you can find out which exact phase transition this is. So this is a technique where you can really combine both, create the high dense material, create the shocks, and then evaluate with the X-rays with diffraction what happens. So that's all I wanted to show you. It's a little bit of a teaser. I've just only scratched the surface of what we can do, but tomorrow, as I said, HLE will scratch a little bit deeper and show you some more science we have done and can do at MEC.
Then let's thank all